Hello Retro Challenge friends. Here's my next update for my Retro Challenge 2021-10 contribution, the Microtronic emulator based drum computer, which is using my re-implementation of the classic 1981 Microtronic computer system. So we already had the drum computer working in previous updates and videos, but the big update in this one really is now that the drum computer is polyphonic now. It can play actually 3 drums at a time, like a real drum computer, right? Previously it could only play 1 drum at a time, per step, per beat. But obviously a drummer has like 2 hands and 2 legs usually, and so I guess I'm not a drummer, but can play up to 4 drums polyphonic at the same time. So we can do 3 now. And let me show you the updated program. And I've made some changes to the user interface, if I may call the LED display like that. So you see here the step count, right? Obviously 16 steps, counting in hex from 0 to F. And now we have the 3 channels here and their current values being played at that step. I made some changes to the drum assignment from 0 to F. So previously 0 was the bass drum, now 0 is actually pause or mute, right? That allows me to erase previously entered steps. I didn't have a mute drum previously, right? So now all the 16 keyboard buttons are obviously used for drums, right? So how do I switch the channels then, right? Because I have no buttons left actually. So for this, I'm using this little jumper wire here, which is connected to 5 volts, right? And it goes to the digital inputs here, the pin header you see there. So there are 4 digital inputs. And if I put high on input 1, I'm inputting channel 1. If I'm putting it on input 2, I go to channel 2, and so on for the 3 channels. So I can select the channel by actually using that jumper wire. Obviously you could also have like buttons here, but I haven't bothered doing that yet. It worked like this as well. So let's start laying down a track in channel 1, right? So maybe we start with the bass drum, which is now at key 1. And sometimes we need a reset for the power of the MIDI module. Obviously it crashed. And there it is. So it had already registered the key presses I made. Let me just erase those by pushing the pause button here. Okay. No, still not erased. So those DuPont wires are a little bit tricky to deal with. Obviously I didn't get 5 volts on the input, but now I do. Okay, we are back to square 0, and now I can start laying down the track. Alright, that's our bass drum. Now let's maybe go with the hi-hat on channel 1, so I'm putting the jumper wire to input 1. How about the snare on channel 3? Play it a bit faster. Still not happy with the snare, so I'm erasing some here. Hi-hat I also don't like yet. yeah, you get the idea. So it's polyphonic and it has 3 channels, and I'm using the input wire to select the channel, and then I have the 0 to erase the step, and the other drums are available from 1 to F. And so how did I store all this, right? Now we have 3 times 16 steps, and in my previous videos I explained that this little microtronic computer has 16 times 2 4-bit registers, right? So how do we fit all the drum steps in there? And you might have guessed it already. For this I made another little extension to the opcodes, right, to the instruction set of that machine. And so I'm trying to explain this a bit using this little whiteboard here, right? I think it's called the boogie board. I like it for scribbling. So so the 16 registers, right, we have here. And there are actually 2 sets of those, right? So there's also the extra set. So they go from 0 to F, and they are 4 bits wide, right? And the extra set is an exact copy of them, and you can exchange the lower part. You can swap them, the lower 8 registers. You can also swap the upper 8 registers. And I used that in my previous version of the drum computer, where I had in the registers, these are the lower ones here from 0 to 7, and those are the upper ones from 8 to F, where I actually use the upper register banks for storing the 16 steps, right? And after 8 steps I would just swap them using the XRM opcode, right? And so the lower registers here were used for controlling basically the program, right? So I had the count and beat number, for example. So that's what I used in the previous drum computer version. But now actually you can tell we wouldn't have enough registers, because for polyphony, right, we have 3 channels now times 16, so we don't have enough registers for this. So how did I achieve this? So now I'm still using, of course, the internal registers, right? But in addition, I now have basically an array storage on the side here, right? And so this has a number basically of addresses or indices. This array currently I have from 0 to F, or 16, right? 15, sorry. Positions here, and the array basically has 3 columns, right? So each of those rows, in each of the columns I can store 1 drum note per beat, right? And now this is obviously something which I extended in the firmware of the CPU emulator of the Microtronic, right? And it's not part of the original, so that won't run on the original Microtronic. But now you kind of need to extend the instruction set, of course, in order to work with that, and you need instructions that do some kind of load and store, right, or architecture similar to RISC. And so what I'm using here is registers 0 and 1. Now basically together they provide the index into that table, right? So for example, if register 0, this is the least significant nibble, and this is the higher significant nibble. So if that would contain a 1 here, right, and a 0, then it would address basically this this row here, right? And it's 3 4-bit values, it's 3 columns. And so, but none of the Microtronic instructions work with that, right? So we now kind of have an address counter in registers 0 and 1 to index the array, but in order to get its values we need another opcode now to actually, you know, copy those, right? And for this I now have instructions that basically can copy in register 3, 4 and 5. So that one would go here, that one would go here, and that one would go here, right? And once we have them in the usual Microtronic registers, I can of course use the existing instructions to do with them whatever we want. And so I have a number of these vacuous opcodes now extended in order to support this. So the index is being loaded in registers 0 and 1, and then I'm using a vacuous opcode basically to fetch the addressed array content and store it into register 3, 4, 5. I have another opcode to store it into 6, 7, 8, and so on, right? And I can show you the opcodes in a minute. But now we have them in the registers, and we can use the non-blocking kin input command basically to change these values, and then we also have basically an opcode to write them back into the memory, right? And finally, I also have an opcode now to increment the address, the index, in one step, right? Of course, you could also do this by hand with the existing microtronic instructions, but I found it useful to have a counter basically, which is aware of the size, the length of the array, right? And then it just, when it reaches the end of it, it just wraps around, right? And so I have a special opcode for this, which is aware of the length of the array and increments and does the overflow also to the register 1 for the, so I don't need to program this by hand, and also don't need to do the size comparison for the overflow loopback by hand. So yeah, and currently, I mean, I can only have 16 times 3 steps in SRAM because I'm running out of SRAM in the Arduino, in the 80MB 328P. Yeah, so conceptually I could also, if I had a larger SRAM, I could also extend this to 32, 64, or any number of basically columns, right, rows, as much as I have memory available. So yeah, this is how this works, and now maybe we can quickly step through the program so you see how it's actually, which opcodes are being used to implement this. And so I'm zooming in a little bit more into the display so we can see it better. Okay, so here's the drum computer source code, machine code. 0 to 2 enable MIDI mode, right? So 3F1, this enables non-blocking keyboard input. So as explained in my previous video, now I'm displaying registers, 4 registers starting from register 4, which is 4, 5, 6, 7. And so now I'm loading basically index register for the array, right? So store a 0 in register 1, store a 0 in register 0, so it starts at address or index 0, 0. I'm also storing a 4 in register 4. In register 4 I'm using for the step count, right? Counts from 0 to 16. So this is going to be a copy of the address in register 0, but due to the display command, I cannot display register 0 and the registers that have my drum nodes actually loaded, 5, 6, 7. So because it only has 6 digits, the last register 7 would be missing. And in my presentation just here on the board, I told you actually that I'm using register 3, 4, 5, but that's not right. I'm actually using 5, 6, 7. Sorry for that. So, and so what we are doing here is now we are loading from the array at the register index in the register 0 and 1. We are loading into registers 5, 6, 7. Now I'm using digital input here into register E, right? So this basically now senses the status of the bit pattern here of the wire, which is connected to high or 5 volts, right? And the value is now 1, 2, 4, or 8 in register E, depending on where we have the wire attached. So, and now depending on how the wire is attached, we need to input into different registers, right, for the 3 channels. So now I'm doing a comparison. If there's 1 in register E, right, so we want to input channel 1, then this is a branch if 0 flag set. So if the value is 1, then we jump to address F. If the value is 2, then we jump to address 14, and if the value is 4 for the third channel, right, binary encoded, then we jump to address 17. As you can tell, we don't have computed jumps, so we cannot just change the program counter and add basically something like the digital input register to it and then jump to that, but we need to do explicit comparison, and then the address is part of the jump opcode, right? Immediate of the branch if 0. So if it's 4, we jump to, then the 0 flag is on, and then we jump to address 17. So otherwise the wire is disconnected, right? And then we jump to basically the main playback routine. This is an unconditional jump. It goes to address 18. So now we are using non-blocking input into register 5. This is where the first channel is stored. And now we have a couple of no-ops, and the reason is that you saw that depending on what channel we are inputting, it takes 1, 2, 3, or 1 or 2 or 3 comparisons and branch if 0 instructions, right? So each of those branches should now run at the use the same time of instructions or clock cycle. So in order to not make it speed up or slow down depending on which channel you're inputting, so you need to make sure that each branch in the branch if wire is set, if channel is input, right, executes the same amount of instructions. And for this we are putting in the correct number of no-ops in order to equal that out for the different branches. So after we input it in register 5 for channel 1, we go to address 18 where the main playback is, right? And then this is for channel 2 input. So if the wire is connected to channel 2, then we input into register 6 non-blocking, and then we only have one opcode, no op, and then we go to 18. Else we have channel 3 non-blocking input into register 7. And now we are already at address 18, right? So there's no op and no go to required, because that is that can already continue now without putting the MIDI data, which is in the current registers for channel 1, 2, and 3, 5, 6, 7. So we are outputting register 5 to MIDI, register 6, and register 7 to MIDI. So these are the 3 drum numbers that are being played now, and those are being executed, you know, fastly enough in a sequence so that they sound as if they were played simultaneously, right? So the machine is not that slow that you would actually hear a significant delay between the 3 different channels. But obviously channel 1 is playing first, then channel 2, then channel 3 is being played, but quickly enough behind each other in a sequence. So now all 3 channels have been played. Now what we got to do is the register values might have changed, right? Because on the non-blocking input, if I push the button, right, then either 5, 6, or 7 register might have changed. So we want to store that back into the array, right? And this is the other direction I try to explain here, right? So the arrow copying the register back into the array memory, right? And this is 3 different columns at the current address. This is what this vacuous opcode does. It's one of the AND immediate opcodes. Basically what it says, and register 6 with F, right, which doesn't do anything. It's an idempotent operation, right? So it stores the current registers 5, 6, 7 back to the current array indexed location. And then we increment now the array index. So this is the 0, 1 register array index or array address increment, right, which I told you about. So I don't need to do it by hand by comparing against the array size and overflowing into register 1 and so on. So that's all taken care of this in one opcode. And again, this is a AND immediate opcode, right? AND immediate with F, register 2, again vacuous, and I'm using this for that purpose. And of course the previous opcodes here that we're outputting, basically the current drum number to MIDI, are also vacuous, right? Move 5 to 5, move 6 to 6, doesn't do anything. So yeah, and then basically I increment, the step number has now been incremented, right, by the increment index, and I'm outputting this to the digital outputs here, so we get a little bit of a light show, right? And then I'm also moving register 0 now to register 4 because we are displaying register 4, 5, 6, 7 on the display, otherwise we wouldn't see the step number which is actually in register 0. Yeah, and then we just loop, right? So yeah, that's the drum computer. Alright guys, thanks for watching.